I think today we'll move a little quicker. All right, so we're in section 1.3 in the book, and we're continuing on talking about functions, right? And so we're dealing, I just want to make sure that you've got this from last chapter, that if we have a function, f of x, right, then you can say that the function f is a set of ordered pairs x comma f of x. Right, so we have f as a function of x, and like I said, the way that we say this is f of x, right? That's typically the way that we'll say that to relay what we're talking about. What that means is we have a function named f. This is just a name. It can be any variable, right? Any name we give it. We can have a function named Danielle, right? Danielle of x, right? And we would just write that out. But we're too lazy to do that, so we just use single letters, right? So f is a set of ordered pairs, and the points that will be on that graph are points of value x, and then some value where we take f of x. So f of x corresponds to this is our y value. Does that make sense to everybody? All right, so that's important. It's critical that we understand that when we're talking about functions. And so x is in the domain of f. And so we would say that x equals the directed distance from the y-axis, right? That's what x represents on a graph. It's the distance from the y-axis along the x-axis, and then not y. We're talking about functions, so this should be f of x. F of x equals the same thing, directed distance, but from the x-axis. And so, given those points, let's make sure that we can find the domain and the range. Does anybody think they got the bonus question about the range on that one problem? My question was, what is for f of x equals square root of x minus 1, what would be the domain for that? What do you have to figure out?
What numbers you could put into x to make it like not a negative number.
Not a negative number, right? So x minus 1 has to be greater than or equal to 0. Everybody agree with that? Right, so x then has to be greater than or equal to 1. That would be our domain. So if we wrote it in that format where we showed you, we could do it like this. That looks more like an 8 than an infinity sign. So we're including 1. That's still terrible. Hang on. I'm trying to write it from the wrong side. Let me move over here. Yeah, that's better. All right, so you could write it like that, or you could say that x is all reals where x is greater than or equal to 1. Either of those would have been acceptable. So what would the domain of this be then? I'm sorry, the range of this be? Range is all the possible y values, right? So if we plug in those values for x, what are all the possibilities? If x has to be greater than or equal to 1, then what are all the possibilities for y?
All real numbers of x, or something like that.
Would it be all reals? Yes?
I think everything from 0 and up.
It can't be bigger than 0. I mean, it can't be less than 0, right? Because this right here will always give us a positive number if x is greater than or equal to 1. So it would be 0, comma like that, or you could say all reals where y is greater than or equal to 0, something like that. Does that make sense? Okay. All right, so let's do an example in the book. That was a bonus question with the range part. And the example in the book that we want to do is example 1 on page 29, and it says, can we find the domain and range given the graph that we have here? So again, the domain is the possible what values?
X
The possible x values. So for this particular graph that we have, does everybody have their book? Do you have yours? Are you able to see it digitally? Okay. All right, does everybody else have a book? So I don't have to draw the graph on board, cool. So for this particular one, what's the possible x values since this is figure 1.8. I'll just draw it real quick. I just won't be as detailed as they are, right? So we've got a point down here which is -1, -1, -5. So we're just going to say that's down in this area. And then we have a point where 4 is here. But we note that it's not a solid dot there. It's an open dot. And it goes all the way up to 2, 4. So 2, we'll say, estimate 4 is about right there. So we got a graph that looks something like this, right? Where this point is -1, 4. Is it 4 or 5? It's actually 5, isn't it? Sorry. -1, -5. And this point here is 2, 4. And this point is 4, 0. So the domain are all the possible x values. And so the x values here only run from where to where? For this graph. Huh?
-1 to 4.
-1 to 4, but do we include both -1 and 4?
No, just 4 because of the open dot.
We do include 4 or we don't? If it's an open dot, does that mean it's there or it's not there?
It's not there.
It's not there.
So we include -1.
We include -1, so we would write it like this. -1, comma, 4, and we put a parentheses after 4 to show that 4 is not included. Okay? Does that make sense to everybody? You could do it the longer way, and you could say it's all reals, right? Or you could say, actually not all reals here, you could say -1 greater than or equal to x. I'm sorry, -1 is less than or equal to x, and x is less than 4. You could write it like that as well. So either of those would be accepted. To me, I get in more trouble when I try to make sure I'm putting my greater than and less than signs in the right way. You know, this is just easier for me to think about, but either one's fine. It's just if you put it like this on a test, I might count it wrong, and then you have to come back to me and say, Mr. Walker, I did it right. And I'm like, oh yeah, you did. Okay, so what about the range? The range are the possible what? Possible values, right? Is Hayden, did you get elected as the spokesman for the class today? No one else is talking. What's going on there, everybody? You guys not awake after the weekend? Hayden's getting all the points here. What are the possible why? That's something else we do, Lily. If you participate in class, you give me feedback and talk to me, give me an answer. Even if your answer is wrong, I might write your name on the board, and then that's an extra point towards your class participation. All right? So what are the possible y values? Let's see if somebody besides Hayden can give me the answer for that. What's my smallest possible y value? -5. Included or not? Yes, right? -5. And my greatest possible y value?
Well, did you like 0 and then the parentheses?
Say it again?
You do 0 and then the parentheses then?
For
the y, but for the second number.
For the second number? So 0 then parentheses like that?
Yeah.
Is that the max y value? Is 0 the max y value? 4 is our max y, right? This is the highest point on the y-axis, so we're looking at the greatest y. But see, that's all right. See, Diego put himself out on a limb there, and he gets his name on board as a result. So, good, but I'm glad you pointed that out, because other people were no doubt thinking that. You know, it's like, well, this is as far as the graph goes, and so this has got to be, but we're talking about when we look at the entire graph, what's the highest y value in the graph, right? So it's actually 4, included or not? It is included, right? So we would put a bracket there instead of parentheses. Does that make sense to everybody?
Yes, sir.
All right, let's look at, let's see, they've got an example number 2, and here we don't have a graph, we're just given a function, right? So this is similar to what we just had on the test. F of x equals x, square root f of x equals square root of x minus 4. What is our domain? Possible x values for that? We know that whatever's under the radical cannot be what? the negative number, so we know then that x minus 4, it's always a good idea to just write down this this inequality so that you don't mess up things. So x minus 4 has to be greater than or equal to 0. Everybody agree? Right? And so then x has to be greater than or equal to 4. And so how about I write that down here using this notation? Would I start with a bracket or parentheses? Bracket. Yep. Who said that? Look there. Lily. Already on the board. First day of class. Excellent job. All right, so we got a bracket, and then we'd start with 4, right? Because that's at the lower end of the spectrum. And then here we're going to have the infinity that I had such a hard time drawing. Bracket or parentheses? You always use parentheses with infinity. Okay?
Why is it that way?
Why is it infinity?
Why is the bracket in like the parentheses?
Because infinity, since there's no end to it, we can't really say here's the final point, and so that's why they always use the parentheses with infinity. But do you understand why it's a bracket here?
No.
It's because it's greater than or equal to.
Oh.
If it had been just x greater than 4, we wouldn't have included the 4. But because it can be equal to 4, we use the bracket. Okay?
Makes sense.
All right. Good question. All right, what about the range? What are the possible ranges here? If it starts with 4, and then x increases from there, what's the possible range? What's our starting point for our y values? We start at 4, so if we plug a 4 in for x, what's y going to be? 0, right? So 0 is our starting point, and it's included. And then as we increase, if we bump this up to 5, we've got 5 minus 4, which is 1, and so then y would be 1, and we could just keep going up and up and up and up because we're going to infinity. So it's really anything from 0 all the way to infinity for our range. Does everybody follow that? Make sense? Okay. Now, we did learn how to learn how to punch this stuff in our calculator. So if you want to, you can try that real quick. Try, on your calculator, you would. We got Stevens working. Thank the Lord. That was a weird one. I hadn't seen that issue before. Yes.
I didn't do a calculator. You got one to speak for them.
You did? Okay, so let's walk through that. So power it on first, right? Hit your y equals button. All right. And then you'll see like y1 equals. You can stick your first function at the top there. Is everybody tracking with me? You have a y equals button at the top left.
Okay, yeah.
Yep. Okay. So where you see y1 equals, type in the square root symbol. That's like function. What was it over? It was over the x squared. Okay, so we're doing the square root of x minus 4. So what you want to do is, after you do the square root function, put parentheses in there because we're going to include x minus 4. For the x, you can hit this button right here, which is x. It's got the x and yeah, there you go. It's that number with all the button with all the 4 symbols on it. X minus 4. Make sure for the minus that you don't put the negative sign, but you actually use a minus sign for an enclosure parentheses, and then you'll hit the graph plan.
Wait, which negative do we use?
All right, so you don't want to use this one down here. Yeah, use minus. It's x minus 4. That's it. Yep. So we'll think about, keep that, look at that, and we'll talk about that in a second, see if that makes sense in relation to what we wrote here. But yeah, close your parentheses at the end. Yeah, and then I'll hit the graph. Cool. Does everybody have it? You got it on yours, John? What you forgot to spread it back up.
Yeah.
Hit insert. Insert is second. See that? Now here. There it is. Cool. Go back again. Okay, so it's probably go to your window. Probably a window setting. Yeah. So in here, change x min to 10, negative 10, and x max to positive 10. So you may have to, yeah, there, go back. One. Here it's a negative. So what you want to do is do negative to 10. You can use it clear or just type it in. And then same thing for y min and y max. Negative 10, plus 10. So your window is huge for some reason. All right, now get graph. There it is. All right. You guys got it? You got it? Cool. What'd you use to do that? Desmos. Yeah, I just heard about that actually. So. Yeah. Wait, minus four, that's right. That's right. No, minus four.
So you got a window, and then you
I'm
use
sorry.
or whichever one.
Close your parentheses.
X max. So
And then hit your
max.
Yeah.
Clear and make it.
Yeah.
There it is.
How would you get to like theta?
Let's make it bigger. That's good.
Would you have to like second hash?
You know, that's what I'm guessing is the way that it works. Is it depends on the context. So the graph is the calculator's smart enough to know which when to put it in. You know. Okay. So everybody got a graph that looked like, right? You were like, I don't know about that one. Where's my red? These markers, they just walk off. Somebody see my marker? Here. All right. So it comes over here. The graph should be like over here at 4, right? It does something like that. So everybody see something like that? So let's think about that. Does that match what we were expecting? We said that the domain, the possible x values, started at 4. That looks right, right? Got a value at 4, and then goes to infinity that way, right? And then the possible y values, it starts at 0 on the y-axis, y equals 0, right? And then goes up to infinity. So our graph backs up what we thought was the domain. So that's one of the cool things about calculators. If you use the graphing functions, you can kind of check the work like that, right? Make sense to everybody? All right. All right, let's move on to, let's see. Okay, so this is good. Now that we've got that graph up, we can actually do something. We're going to learn about something called the vertical line test. So remember last chapter, we would look at a problem and we would determine whether or not a graph or a set of points could actually be a function. And so what was the no-no when it was what were the things? One of the key things that would make it not be a function. Let's say we had a set of points. What were we looking for to determine whether or not it was a function? Yes?
Like, doesn't give you 2 answers.
Doesn't give you 2 answers. All right, you're right, but I need you to elaborate more on that. Yes?
It doesn't match like 2 different inputs or outputs. I mean, the inputs don't like.
The inputs don't match 2 different outputs. Exactly. Yep. So Stephen's onto something there. So from a set of points, you know, if I've got just a bunch of random points like this, what is this a function? No. And which 2 points, first, second, third, or fourth, which 2 points make it not be a function? Huh? First and third, right? Because, to Stephen's point, we have the same input, or the same x value. We're looking at points, right? But we've got 2 different outputs, 2 different y values. And so if you have a set of points and you have the same x's but different y's, then it can't be a function. So if we think about that from a graph standpoint, what that means, like if we were to plot these points on a graph, 1, 0, so let's see, just do. So 1, 0 right here, 2, 1 right here, 1, 3 right here, and negative 1, 3 down here. This is kind of a weird function. But let's just say the function the graph looked like that there. Okay? When we went through all those points.
Wait, wouldn't it? If it's negative 1, 3, wouldn't it go up?
Yes. Again, I'm testing you guys. So good catch. Good catch. That's gonna make it really. I'm gonna have to change that. We're gonna change it to just so my point. It'll be like a more normal looking graph. We're gonna change it to -1, and we're gonna say that it's -1, -1. Right? How about that? All right. So if I look at this, the points that have the same x value, I can draw. If I connect those dots, it makes a vertical line through my graph. You guys see that? And so this is what we call the vertical line test. I can verify whether or not a function is, if I see a graph, I can verify whether or not it's a function by asking the question, can I draw a vertical line that goes through 2 or more points on my graph, right? If I can't, then it's a function. So like for this guy here, there's nowhere that I can draw a vertical line, right, that's going to pass through more than 1 point, so that's a function. But here, there's multiple places I can draw a vertical line. You don't have to have multiple places, you only have to have one spot. But there's multiple places I can do that vertical line. And that means that it's 2 points with the same x value, so it can't be a function. Does that make sense? All right, pretty simple test. So you can kind of eyeball, there's a couple of, example 3 in the book has a couple of functions, and they do one function that looks like this, right? And then they have another function that looks like this. And they ask the question, are those, I'm sorry, I used the term function, a couple of graphs that look like this. Is the first one a function?
No.
It's not, because it doesn't pass our vertical line test. A bunch of places that we can put a vertical line that passes through 2 or more points. What about this guy? Yes, right? It's kind of like a sine function there. No matter where I draw my vertical line, I only go through 1 point. Yes?
So pretty much any time the function like both points, you can just look at the y-axis, right?
Yeah.
If it just goes through the y-axis, like that's a vertical line.
Well, I mean, sometimes though, you know, we may have a function like this. It's not really, it doesn't cross the y-axis. Right? But you can use the y-axis for your vertical line guide, right? Just if you draw another line that is parallel.
So basically sideways. Not function.
Yeah, exactly. You can kind of think about it like that. All right?
Okay.
Okay, cool. Any questions about vertical line tests? All right, let's see. Let's move on to definition for increasing, decreasing, and constant functions. What does that mean? It's so exciting. I like to tell the title, you know, you guys are like, ooh, I don't know what that is. I can't wait to find out. You're like, no, I'm not thinking that at all, Mr. Walker. Not at all. Thinking lunch cannot get here fast enough. All right, so increasing and decreasing functions. Let's talk about that. An increasing function is increasing function on an interval for any, we're going to write the like weird, you know, math definition, and then we're going to do an example so that the math definition makes sense. For any x1 and x2 where x1 is less than x2. Right, so we got 2 x values, but one's less than the other. Then f of x1 is less than f of x2. So if we think about that in terms of, I'll let you finish writing that down, and we'll talk about it in terms of the graph. I should have really put my increasing function, we'll put that back here. You're like, I didn't put it there though. I'm going to put it there just so I can rewrite all that stuff for decreasing. So what that means, if we look at it on a coordinate plane, is that our graph is doing that. Okay, it's going, if you think about what we said here, if this is x1, right, and this right here is x2, then the y value, which is f of x1, is less than the y value f of x2. Okay, so what it means is that a portion of the graph is increasing if basically it's going up as you go from left to right. Does that make sense to everybody?
Does that say on or in?
On the interval, that does say on, but that's not, doesn't make any sense. It's what it was supposed to say was increasing on, so I'm just going to say on in interval. Yeah, and will work. So an interval for any x1. Thank you. I totally write your name on the board for that, Steve. Right there. All right, so let's do decreasing. As you might expect, it's just the opposite of that. So all of this language is pretty much the same, right? Our x1 and x2 are related to one another the same. So it's only going to change when we get down here, and it says that f of x1 is greater than f of x2. And so that, of course, just means we have a graph where this portion of the graph looks like this, where this is x1 and this is x2. So as we go from left to right on the graph, the y values are going to go down, they're going to decrease. So as long as you think about the increasing portion or decreasing portion as referring to what the y values are doing, then that'll help you remember that. So who wants to take a guess for this last one here, the constant portion of the function, what symbol I'm going to put in between f of x1 and f of x2? Yes? Equal sign, right? So that just means we have for x1 here and x2 here, we have a horizontal line, right? So they've got a few examples in the book. I'll just do one of those for time's sake. Negative 1, 2. Got a point here, negative 1, 2. And we got a point here at 1, negative 2. And this graph does this number here. Oops, I totally drew that wrong. All right. So the question here, it says determine the open intervals on which each function is increasing, decreasing, or constant. So for the increasing portion of this graph, which portions are increasing? Could you give me a range, like we would do, and it says open interval, so like we might do something like, negative 2 to 3 or something like that. Who could give me an interval for the increasing portions of this graph? What am I looking for as far as increasing goes? It's rising as you go left to right. So you think you know that one, Lily?
Negative infinity to negative 1.
Negative infinity to negative 1, she says. And this is a 1, this is a 1, 2, negative 1, negative 2. Everybody agree with that? Do you guys see that? You see from here up to negative 1 for those x values, right? Our graph is increasing. I agree with that. Is that the only place it's increasing, though? It's not. So what's the rest of it?
1 to infinity.
So 1, also 1 to infinity. All right, so those are the x values along which this function is increasing, right? Our y values go up as we go through that range, or that domain, actually, is what I should say. What about the decreasing portion? Somebody besides Lily. Yes, Stephen, take a stab at it.
Negative 1 to 1.
Negative 1 to 1. Well, we agree with that. And so notice for all of these, we always do these as an open interval. Right? We use parentheses instead of brackets on these. And the reason why is because You know, once you hit that exact point there, well, what do I call it? Do I call it increasing or decreasing right there? It's changing direction. And so we don't include that point in it because it kind of functions as both. It's part of our increasing portion, and it's also part of our decreasing portion. Okay? Let's do another one. What if I have something like this? We'll say this point is 1 here, and we'll say this is -2, and we'll say this is, we'll do it like this. We'll say this is +2. So what would be my increasing portion? Is everybody done writing the last one down? Sorry. You good? Everybody good? All right, so what would be the increasing portion for this graph?
We're talking about our X values, right?
The X values, that's right. So when we're talking about, let's think about it, the definition of increasing only has to do with the X values and then what the resulting Y's are, right? So for this, the X values would do what for increasing?
Negative infinity to -2.
Negative infinity to -2. All right. The decreasing portion, we don't have any. Do we have more increasing? I do. So what else goes under that?
2 to infinity.
2 to infinity. And this time we don't have any decreasing, but we do have a constant portion. So our constant portion would be what? Go ahead.
-2 to 2.
-2, 2. And again, just make sure, the key thing here is make sure that you use the parentheses, right? It's an open interval. Very good. All right, any questions about increasing, decreasing, constant? All right, let's talk about relative minimum and maximum values. And so the idea with this, let me just draw the graph first, because I think it'll make sense to us when we see a graph of it. Better probably than writing out the definition. So if I have a graph that looks something like this, just erase these things. So let's say we have a graph that looks like that. The relative minimum and max values here has to do with the low points and the high points on the graph. Okay? So like for this particular graph, I have a low point here and I have a low point here. So everybody see that? And what I would refer to these as would be relative minima. So for this portion of the graph, right, we have a dip down here and we have a dip down there. So those points are minimum points compared to the other points around it. All right? And so this, of course, would be relative what? What do you guys think? If this was minima, then it's a Nissan car. The maximum, that's right. Relative maximum. So we could write this down as a formal definition, and it would say, just to kind of think through it, it says a function value f of a is a relative minimum of f when there exists an interval x1 to x2 well, I clearly left something out in what I wrote down here. Give me a moment. Oh, that contains A. That contains, all right. This was a terrible, they shouldn't have used A. I hate to swap this up on you guys. Can we do this? Can we say f of b? Because this looks really weird when you write it out, unless you could do like nice italicized a like they did in the book. A function value f of b is a relative minimum of f when there exists an interval x1 to x2 that contains b. All right? So this is our b that's in our f of b here, such that x1 is less than x is less than x2 implies f of b is less than or equal to f of x. And that's a whole lot of stuff to say. But it's the definition in the book, and I just want to make sure that you guys, when you read something like this, that you can kind of track what their point is with it. So I'll let you finish writing that down. So b is just a value for x, right? F of x is some random value of b. Like in the case right here, it would be f of 0, right? B would be the value 0, but they're using a variable here, so it can be any value of x. So f of b is a relative minimum. So we could say this point b on the x-axis is a relative minimum of f when there exists an interval x1 to x2 that contains b. And so we could say, for example, this was x1 and this is x2 that contains b such that x1 is less than x is less than x2. So the value x1 is less than x2, right, on the graph. This range here, this value is smaller than this value here. And then it implies that f of b is less than or equal to f of x. So for any other value that you plug in there over that range, f of b is either going to be less than that or it's going to be equal to it. So that's a really complicated way to say that the graph dips down, right? And it's a low point of the graph.
Yeah.
But if you guys are reading this in the book, right, I want you to be able to make sense of that. Because sometimes understanding what they mean by these definitions is really, really convoluted. So, and the opposite is, and I'm going to write this in a little simpler way, it's a relative maximum, since we've already got that first definition there. So relative maximum when x1 is less than x is less than x2 implies f of b is greater than or equal to f of x. So it's just kind of the reverse of what we said for the minimum. And I'm going to make a note here. Change my notes to f of b. Okay, so I'm not going to spend much time on that. I think you can see that in the graph. It's just kind of obvious. What about the definition of a piecewise function? A piecewise function is just where the easiest way to probably think about this is just graph 1. There's an example on page 8. And it says graph the following. F of x equals 2x plus 3.
Example.
2x plus 3, this is on page 34. Yes?
Do you mean example 8, not page 8?
Sorry. Example 8, page 34. So 2x plus 3. And I'm going to write it down. Where x is less than or equal to 1, and negative x plus 4, where x is greater than 1. And so all this means is that this is called a piecewise defined function. Bless you. It is a function, right? It passes all the rules for function. We can do a vertical line test after we graph this, and we can see that it's that there's no vertical line that passes through there. But it means that our graph is going to be in pieces, right? For a certain interval, the graph is going to look like this, and then for another interval, the graph is going to look like this. So let's just see if we can graph this real quick. Is that what it says to do? Yeah, sketch the graph of it. So we've got our x and y axis. And it sure would be handy if we just had a section of the board that was already set up as a graph, and that'd be nice. I guess I could just like put one on the TV and then I could draw it on the TV, right? I won't have any problem with these markers coming up. No issue there. So let's see the first one. So for x is less than or equal to 1, so let's punch in 1 here in this first one. Let's insert 1 here to see what we would get. So when f of x, if we do f of 1, right, we get 2 times 1 plus 3. So that's going to equal 5. Everybody agree with that? So I just took the first part there, because x can be equal to 1 in that one, inserted 1 into this function here, and I got the value 5. So we know that for this portion, that point 1, 5 is going to be on that graph. All right? So I go 1 here and go up to 5 right here. And just so we can get another point, we know this is going to be a line because it looks like our equation for a line. What's our slope-intercept form for a line? Y equals mx plus 3. So for this one here, if y equals mx plus 3, it's y equals 2x plus 3. So we have a y-intercept of 3. So we can put a dot here. We have a slope of 2. So rise over run is 2 up 2. And then our run is an understood 1 here because 2 is the same as 2 over 1. So that works here. Up 2 over 1. So we can go down 2 and over 1 here. So this would be this portion of the line. But notice I was careful to not draw it that way because x can't be greater than 1. X has to be less than or equal to 1, right? When we talk about x greater than 1, we've got to look at our other function for a line. And so if we plug in 1 here, f of 1 for this is negative 1 plus 4. So that's going to be 3. So we've got a point 1, 3 here. But it can't actually be that value. So when we plot 1, 3, we're going to have to put a circle there, an open dot, right? To show that it doesn't include that point. And so then we can look at the equation for a line, y equals negative x plus 4, and see what the line is going to do as x increases. We could just kind of pick a random point, x plus 4. If we pick the point, well, 4 is our y-intercept. But we can't go that way because the y-intercept is here, so we need to go to the right. So I'm going to plug in the value 4 here so we can see where it's going to cross the x-axis. So I'll plug in 4, y equals negative 4 plus 4, or y equals 0, right? And so we know that there's a point right here. And so what this function is going to do, this line is going to do is it's going to go that way. So you just have to make sure that whatever direction you draw your graph in, your line in, or whatever type of graph it is, that you're staying within the domain that's been defined for us. Does that make sense to everybody? I hope I explained that correctly. Yes.
So why did you put a positive? Why did you add positive 4 to make it 0 again?
What, right here?
Yeah, why did you put a positive 4?
Well, because I was just putting in an x value that would be easy for me to work with here. So I knew if I put in a positive 4 there, that just the math was going to be simple and I was going to get y equals 0. And so I knew it was going to cross the x. I could have done anything. I could have put in a 2 there, and which would have given me y equals 2. right? So if I put in a positive 2, it would have been y equals 2, and I'd have gotten this dot here. I could have drawn my line that way. It was just a simple number.
Yeah, just because the domain is x.
It's got to be greater than 1. All right, so I had to pick a number that was greater than 1. That's a good question. Does everybody follow that? Why I picked that value? Again, this is something you can plug in your calculator and kind of check it, right? And so that's why I want you guys to understand how your calculator works, because this is the type of stuff that will help you be able to check your work. If I ask you to do this on a test, I'm going to want to see this type of work here to make sure that you understood it. But your calculator is a great way to check it to make sure that you didn't make a mistake. If you punch it in your calculator and you're like, wow, that graph doesn't look anything like what I came up with, let me redo my math over here and make sure I didn't make a mistake somewhere. Okay? All right, last thing here in this chapter is an even-odd function, and even-odd functions just have to do with symmetry around a particular axis. And so this is what the definition for even-odd function says. Function whose graph is symmetric with respect to the y-axis is an even function. All right? So for example, just to draw a little quick example, a graph that does like this here. You see how that's symmetric about the y-axis? Whatever you have on the right side of the y-axis, you have a corresponding point on the left side of the y-axis. So you can kind of flip it around. If you flipped it around the y-axis here, it would look the same. So that's how we test to see if it's an even function. And we can algebraically test if this is an even function. Even function test. By doing the following. Does f of negative x equal f of x? And so let's think about what that means. Let's say we got a point 1, 1, 1. All right, so here and here. And so in this case here, this is -1, this is +1. We'll just say this is 1 right there. So for f of negative x, f of -1, does f of -1 equal f of +1? And we see that it does. In both cases, the y value is 1, right? So that's our algebraic test for an even function. If it's symmetric about the y-axis, then for every negative x value, there will be a corresponding positive x value that have the same y value at that point. Okay? A function whose graph is symmetric with respect to does anybody want to take a guess with respect to the what is going to be an odd function?
The origin.
The origin. Yes, who said that? Yes, very good. I was really hoping someone was going to say the x-axis, and I was going to make so much fun of them. Oh, it wasn't even going to be funny. Why can it not be about the x-axis? What is it? What if I have a function that looks like this that's symmetric about the x-axis? What's the problem there? It fails the vertical line test. It's not even a function, right? So it's symmetric about the origin. I was only going to make fun of it. It was going to be hilarious. You're going to think it's so funny when I did it, right? Nobody's going to be crying. All right, so let's see what an example graph would be for that. It would be something that looks like this. That value, that there. So you could flip it around the origin and you get the same graph. And so what this means algebraically is that f of negative x has to equal, here's the test. Does f of negative x equal negative f of x? So for this one here, again, let's say we have, -1, -1, and then there's a point here, and then we've got +1, +1 there. And we see that if we try f of -1, f of -1 equals f of -1, so when x is -1 here, that equals -1. But if we do f of 1, then that value is 1, right? And so we see that this is proved. F of -1 equals negative f of 1. So if we were to actually punch that in, f of -1 equals negative f of 1, and we said f of 1 equals 1, so it equals -1. And that's exactly what we saw to be the case. So you should be able to plug in values and prove this to test if it's an odd function. All right? Wow, time just goes by. It's crazy. All right, we're going to blast through 1.4, all right? Because 1.4 is not terribly hard. You're like, no, right? What 1.4 is all about is transformations of graphs. And so there's some parent functions that we need to know the graphs of. And if we know the graphs of these parent functions, then we can change. I can give you a new function, which is really just a variation of the parent function, and you can figure out what the graph is going to do because you're familiar with the parent function. So there's kind of 6 functions, 6 common parent functions that are mentioned on page number 41. All right, and they are this function here, which is f of x equals x, just a straight line through the origin, right, with a slope of 1. That's a linear function. There is the absolute value function, which looks like this. All right, so that's f of x equals absolute value of x. There's the square root function, and we've already done a variation of that. We looked at a transformed version of the square root function, but it looks like this. We punch that in our calculator, f of x equals square root of x, square root function. And we have the quadratic function, which looks like that. Is that an even or an odd function?
Even.
Even function, symmetric about the y-axis. That's the quadratic function. And then, I'm going to put it up here just to make sure everybody can see it. We have the cubic function that looks like this. I didn't draw that very well. That's f of x equals x cubed, cubic function. And then finally, the rational function, which looks like this. of x equals 1 over x. All right, so there's all of our parent functions, all right? And we can punch in values here and actually plot points and recognize, things like, if this is absolute value of x, then I know that if I have a point 2 here, that the value is going to be 2, and if I have a point -2, the value is going to be 2 there. So we can actually put points on there, and we will do that once we start transforming them. But you need to recognize the pattern. You can plug in really simple x values to figure out where to plot some points and make sure you're going through the right location and all that. But I'm going to talk about transforming some of these parent functions, and the first thing that we want to talk about is vertical and horizontal shifts. So vertical and horizontal shifts work like this. Vertical and, I'm going to just abbreviate, vertical and horizontal shifts. And so if C is a positive real number, then shift y equals f of x in this manner, or in this way. Vertical shift C units upward when you have h of x equals f of x plus c. So what that means is, let's just do, for example, we'll just pick a function each time and shift it according to what it says here. If instead of f of x equals c, if I change this, f of x equals x, if I change this to f of x equals x plus 2, right? So 2 is our c value here. Then what it means is we take the whole graph and we shift it up 2 units. All right, so instead of where it is here, then I've got 1, I've got 2, so it's going to go through 2 and be a line that's parallel that way. Just shift it up 2. Yes?
If it's negative, can you shift it down? Or is it
Yeah, that's the next one. So the next point number 2 is, like you said, just the reverse of that. If c is negative, then it goes down. All right. So we'll go ahead and write that down. Is everybody clear though on that shifting, how that works? That would work for any of these functions, right? If I said f of x equals the absolute value of x plus 2, if I put a 2 on the outside of the absolute value, then my absolute value function would shift up 2 units. All right. We'll save that for another one. Maybe we'll do that for the next one here. All right. So vertical shift. C units downward when h of x equals f of x minus c. So we'll do that here. If I did this as minus 3, then I would go 3 units down, and it would look like that. Negative 3. Does everybody see what I did here? Just make sure you weren't writing down that I modified my absolute value function there by shifting it downward. Now we do a horizontal shift. Horizontal shift C units. This one's a little bit tricky. To the right when h of x is equal to f of x minus c. And I say it's tricky because right is the positive direction on the x-axis, so we would kind of expect this to be an x plus c here, but it's not. It's an x minus c. All right? So what's different about that is it's not we didn't put the minus c outside of our function like we did right here. We're gonna replace x with x minus c. So what this means for this one here is basically it's the difference between f of x, f of the absolute value, f of x equals the absolute value of x minus 3 versus f of x equals the absolute value of x minus 3. That's a different function. All right? So this one, this function here corresponds to point number 2. This function here corresponds to point number 3. You guys see that? One, I replaced x with x minus 3. On the other one, I put the minus 3 outside of where the function that x was in. All right, so what this function looks like here is we would take this guy here and we would shift it. We'd shift it 3 units to the right. So this would be our starting point, and it would be like this number here. Okay? Yes?
So if the 3 were positive, would it go back?
Here we go left. All right, you guys are just ahead of the game. Nice job. That's what our fourth point is. Why am I even here, right?
So the fourth one is just horizontal shift C units to right when h of x equals f of
C units to the left
Change to the left, yeah.
Yeah.
H of x equals f of x.
plus C. Yep. All right. So that, like I said, you guys see how that could be kind of confusing because you would think the negative would take it to the left, but it doesn't. The negative C takes it to the right.
That's like the most important thing, right? Just remembering that negative is to the right and positive is to the left.
Exactly. H of x equals f of x plus C. So I think you guys have that down, so I'm not going to do an example of that one. But I do want to ask, are there any overall questions about those steps, how you would shift the parent function? This was a biggie. I want to make sure you guys understand the difference between this. Everybody tracking with me here? The difference between absolute value of x minus 3, where the minus 3 is outside the absolute value versus when it's inside the absolute value. If that makes sense? So if I shifted, for example, this one, if I wanted to shift this graph here 4 units to the left, what would I change it to? That would be f of x equals what?
X, or what you said to the left.
Yeah, and maybe I should do this. Maybe I should just write it down there. If it's to the left, then 4 units to the left, then I would write that as f of x plus 4, right?
Yeah.
And so what would this new function be? It'd be x plus 4, all of that in parentheses, cubed. All right? You guys see that? But what if instead of moving it to the left 4, I wanted to move it up 4?
What we do, then the equation would be f of x, it's f of x, you said up, right? So f of
Up
x
4.
plus 4 on the outside, and then the equation would be x cubed plus 4.
Right? On the outside of the x cubed. Okay? You guys got that? All right, one more thing. I'm going to tell you guys one more thing, and
4 minutes.
this is reflecting graphs. Again, these are pretty easy concepts as long as you're tracking with it here. Let's talk about reflecting graphs. And this is what reflecting graphs say: is that if y equals f of x, then y equals f of x will be reflected as follows. One, reflection in the x-axis when h of x equals negative f of x, and a reflection in the y-axis when h of x equals f of negative x. So that means that if I have a if I do negative, if I take, let's say we take the quadratic one here. If I want to graph f of x equals negative x squared, that's this here, right? So it reflects about the x-axis, and so the graph then becomes, I'll do this in green so we can see a difference here. The graph then becomes this. It reflects about the x-axis. What if I wanted to make that reflect about, well, the thing about that one is it's already an even function, right? So it's symmetric about the y-axis. So if I try to flip that one about the y-axis, it's going to look exactly the same, right? So let's think about this one. Ooh, no, we don't want to do that because it's negative under a radical. We can do the first one. So f of x equals x plus 2. If I said, well, x plus 2 is what I did before, but if we go back to just f of x, we have this graph here. If I said, instead of f of x, I'm going to do f of negative x, right? So that would be a negative x like that. This is a bad example because it doesn't matter how we do it. The graph is going to always look the same because it goes through the origin. So it'll look the same whether we think about it this way or this way, because in both cases we still have f of x equals negative x, right? So we can do it with this one. Yeah, this one changes, right? This one, sorry. This one here, how about this? F of negative x equals, if we replace the negative x here, right? Then that means that it's going to be reflective around the y-axis. So then this guy moves over here, so this comes this way, down like that. Does everybody see how I flipped that about the y-axis? Some of these you'll get the same thing. You know, like I said, for this one here, this is actually exactly the same as negative f of x. Negative f of x equals negative x cubed. It's just we think about it not as reflecting about the y-axis. We think of it as reflecting about the x-axis, but the graph ends up looking the same if we're reflecting about the x-axis. Okay? All right, so you guys do problems associated with that. There was one other concept where we could stretch the graphs. And we stretch the graphs by putting a number in front of it. So like instead of x squared minus 3 or x minus 3 squared, we did something like this, 3x squared. We put a number in front and multiplied it by that. That will actually stretch the graph. So if it's a number that's bigger, it's 1 or bigger, it will stretch it. But if it's a number that's smaller, between 0 and 1, if it's a decimal or a fraction, then it will shrink it down. It'll maintain its same basic shape, but it'll either be shrunk or stretched. So that's the last concept. You're going to have some homework over that. All right. So you guys, we just ran out of time for going through the last part. You can read in the book, and if you're confused about it, you can answer some questions about that at the beginning of class next week. Okay. All right. You guys have a good day. Sorry I kept you a couple minutes late. Thank you.